There is a problem that has been quietly haunting the most ambitious technology project in human history. Scientists have known about it for decades. They have written papers about it, built entire research programs around it, and spent billions of dollars trying to work around it. And for most of that time, the honest answer to the question, when will quantum computers actually change our lives, has been some version of, not in your lifetime. That answer just changed. A team of researchers at the University of Chicago published a breakthrough that does something most experts considered impossible in the near term. They found a way to slash the number of physical components a quantum computer needs to perform reliable calculations by a factor of 10 to 20. Not 10 or 20%, 10 to 20 times. The kind of reduction that does not just speed up a timeline, it fundamentally rewrites what is possible and when. To understand why this matters as much as it does, you need to understand the problem they solved. And the problem goes much deeper than most people realize. Quantum computers are not faster versions of regular computers. That framing misses the point entirely. A regular computer, whether it is a phone, a laptop, or a supercomputer the size of a warehouse, works by manipulating bits. Every bit is a tiny switch, either on or off, 1 or 0. All of modern computing, every email, every transaction, every simulation, every piece of software ever written, is built from billions of those simple on-off switches firing billions of times per second. A quantum computer does something fundamentally different. Instead of bits, it uses quantum bits called qubits. And qubits do not have to be either 1 or 0. They can be in a state called superposition, which means they can exist as both 1 and 0 simultaneously until the moment you measure them. That is not a metaphor or a simplification. That is a real physical property of quantum systems, and it is one of the strangest and most powerful things in all of science. When you connect multiple qubits together through a quantum property called entanglement, something remarkable happens. The qubits begin to behave as a single interdependent system. The state of one qubit is instantly correlated with the state of others, regardless of how far apart they are. And when you build a quantum algorithm using entangled qubits in superposition, the machine does not check possible answers to a problem one at a time the way a regular computer does. It explores enormous numbers of possible answers in parallel, all at once, and then uses interference effects to amplify the correct answer above the noise. The result, in theory, is a machine that can solve certain classes of problems that are completely beyond the reach of anything built from ordinary transistors. Not just harder problems, different problems. Problems that classical computers cannot solve in any reasonable amount of time, no matter how powerful they become. And the list of problems in that category includes things that could reshape entire civilizations, designing new drugs and predicting exactly how they will behave in the human body. Cracking the encryption systems that protect every bank account, every private message, and every government secret on the planet. Modeling the quantum behavior of new materials to discover better batteries, better solar cells, and better superconductors. Optimizing global logistics networks in ways that could meaningfully reduce fuel consumption and carbon emissions. And potentially accelerating artificial intelligence into capabilities that make today's systems look primitive. The promise has always been enormous. The reality has always been that we cannot get there yet. The reason why brings us back to the core problem. Qubits are among the most fragile objects in the universe when it comes to holding information. A regular bit, sitting inside your phone or computer, can hold its value for years. You could drop the device, take it through an airport scanner, put it next to a speaker blasting music, and those bits would still be exactly where they were. They are stable, robust, and essentially impervious to their environment. Qubits are the exact opposite. They are so sensitive to their surrounding environment that tiny fluctuations in temperature, barely perceptible vibrations, stray electromagnetic signals, and even the random motion of nearby air molecules can knock a qubit out of its quantum state. When that happens, the qubit loses the information it was holding and makes an error. Scientists call this decoherence. The qubit's quantum state collapses before the computation is finished. Here is what makes decoherence so devastating. A useful quantum computation does not involve a handful of qubit operations. It involves billions of them. And if each individual operation carries even a small probability of failure, the errors compound. By the time you have run billions of operations, the accumulated errors have corrupted the result beyond recovery. You are not computing anymore. You are generating noise. The best quantum computers available today have physical qubit error rates of roughly 1 error per 1,000 operations. That sounds like a small number until you think about what it means at scale. Imagine trying to send a text message where every 1,000th character randomly changes to a different letter. For a short message, you might still understand it. But for a message that is 1 billion characters long, the original meaning is completely gone. That is the error problem in quantum computing. And it is why researchers have long believed we were decades away from machines capable of doing anything truly useful. The engineering solution they developed is called quantum error correction. The idea is conceptually straightforward, even though executing it in physical hardware is brutally difficult. If you cannot prevent errors from happening, you detect and fix them as they occur. The way you do this is by taking the information you want to protect and spreading it across many physical qubits at once. Instead of one qubit holding one piece of information, you take that single piece of information and encode it redundantly across hundreds or even thousands of physical qubits working together. This collective group acts as a single reliable logical qubit. If one of the physical qubits makes an error, the others can detect it through a series of measurement operations and correct it automatically before it propagates. It is not entirely unlike the way airlines maintain aircraft. A commercial plane does not fly with a single engine because a single engine failure would be catastrophic. It flies with multiple engines so that if one fails, the others keep the aircraft airborne. Quantum error correction uses the same logic. Redundancy is the price you pay for reliability, but here's the part that created the crisis. The redundancy required is staggering. The most widely used quantum error correction approach, called surface codes, requires roughly 1,000 physical qubits to protect a single logical qubit at a level good enough to be useful. And a meaningful quantum algorithm, the kind that could actually do something a classical computer cannot, needs not one logical qubit, but potentially thousands of them. Do the math. Thousands of logical qubits, each requiring 1,000 physical qubits for protection. You need millions of physical qubits before a quantum computer can do anything that matters in the real world. Today, the most advanced quantum processors have a few thousand physical qubits at best. The gap between where we are and where we need to be is not a small engineering hurdle. It is an enormous gulf. That gap is why serious, credible scientists who are not pessimistic by nature were saying 30 years. Not because the physics is wrong, but because the manufacturing challenge of building millions of reliable, interconnected quantum hardware components with current technology is genuinely overwhelming. This is the wall that the University of Chicago team found a way through. The research came from the Pritzker School of Molecular Engineering, and it was published in the journal Nature Physics. The team was led by Professor Liang Jiang and included collaborators from Harvard, Caltech, the University of Arizona, and critically, a company called Quera Computing, which is one of the most active developers of real quantum hardware in the world. The involvement of an actual hardware company in this research is not a minor detail, and we will come back to it. The breakthrough centers on replacing the standard error correction approach, surface codes, with a different class of codes that the quantum computing community has known about theoretically for years but could never actually use. They are called quantum low-density parity check codes, often abbreviated as QLDPC codes. To understand why switching to them is so significant, you need to understand what makes surface codes so inefficient. In a surface code, physical qubits are arranged in a two-dimensional grid, like a checkerboard. Error detection happens by having each qubit check itself against its immediate neighbors. If a qubit makes an error, the surrounding qubits can detect an inconsistency and flag it. The system works, but only in a very localized, short-range way. Each qubit can only see what is happening right next to it. Think of it like a neighborhood watch program where every participant can only observe the two houses directly next to theirs. If someone suspicious is 3 streets away, nobody in the watch can detect it. The system works, but the coverage is local and expensive. To protect a large area, you need enormous numbers of participants, and most of them will be watching the same small patch of territory over and over without adding much value. QLDPC codes work on a completely different principle. Instead of checking only immediate neighbors, qubits compare themselves to other qubits that may be far away, spread across the entire system. Using the same neighborhood watch analogy, this is like giving every participant a pair of high-powered binoculars and a radio that lets them communicate with people on the opposite side of the city. Suddenly, a much smaller group of people can effectively monitor an area that would have required 10 times the participants under the old system. The coverage is no longer limited to local proximity. It extends across the entire network, and the whole operation becomes dramatically more efficient. And the mathematics behind QLDPC codes has been understood for years. Researchers knew they were theoretically superior to surface codes. The problem was physical. In a standard quantum processor, qubits are fixed in place. They are embedded in solid hardware and cannot move. They can only interact with their immediate physical neighbors. Getting 2 qubits on opposite sides of a chip to communicate directly with each other requires some kind of connection between them. And building those long-range connections in quantum hardware without introducing new and worse errors was considered essentially impossible with existing architectures. The theoretical advantage of QLDPC codes was real and understood. The physical implementation was a wall nobody could see past. The University of Chicago team found the door in that wall. Their solution was to stop thinking about qubits as fixed objects embedded in hardware and start thinking about them as particles that can be physically moved. Specifically, the team developed a blueprint using what are called reconfigurable atom arrays. In this approach, the qubits are not transistors etched into silicon. They are individual neutral atoms, real atoms, held in place by beams of laser light. The lasers act like extremely precise tweezers, trapping atoms at specific locations in a three-dimensional space. Here is what makes this revolutionary. Because the atoms are held by light rather than locked inside solid material, they can be physically relocated. The laser beam holding an atom can be adjusted to carry that atom to a new position within the quantum processor. You can move a qubit from one end of the system to the other. This means that when a QLDPC error correction operation needs 2 qubits to communicate across a long distance, you do not need to build a physical wire connecting them across the chip. You do not need to route a quantum signal through intermediate qubits, each of which adds its own error risk. Instead, you simply move one of the atoms to where the other one is, let them interact at close range, perform the necessary error checking operation, and then return the atom to its original position. Distance becomes essentially irrelevant when you can move the participants. The long-range communication problem that had blocked QLDPC codes from practical use for years vanishes because you're no longer asking information to travel across a chip. You are physically transporting the qubit to where it needs to be. The results of combining QLDPC codes with reconfigurable atom arrays were more impressive than even the research team had initially projected. Under the standard surface code approach, running a quantum algorithm that requires several thousand logical qubits demands millions of physical qubits to provide sufficient error protection. Using the new QLDPC blueprint with movable atom systems, the same algorithm could potentially run with fewer than 100,000 physical qubits. The reduction is between 10 and 20 times fewer physical qubits needed to achieve the same computational result. That is not a marginal improvement. It is not a modest tweak at the edges of a problem. It is a complete re-architecting of what fault-tolerant quantum computing requires. The difference between 100,000 qubits and 1,000,000 qubits is not just a manufacturing challenge. It is the difference between a machine that the best engineering teams in the world can plausibly build in the next several years and a machine that might not be achievable for several decades. And this is where the real-world implications start to become concrete and personal. Consider medicine first, because the human stakes here are the most immediately compelling. One of the most computationally expensive problems in all of science is simulating the quantum mechanical behavior of molecules. When a pharmaceutical company wants to develop a new drug, they need to understand exactly how a candidate molecule will interact with specific proteins or enzymes in the human body. These interactions happen at the atomic scale, governed by quantum mechanical forces that cannot be accurately modeled by any classical computer for anything beyond very small, simple molecules. This is not a theoretical limitation that will be overcome by building faster supercomputers. It is a fundamental mismatch between the nature of the problem and the nature of classical computation. Modeling quantum mechanical interactions accurately requires quantum computation. Without it, drug developers are essentially working blind, testing enormous numbers of candidate compounds in expensive laboratory experiments and clinical trials, most of which fail. The average time to bring a new drug from initial concept to market approval is over a decade, often closer to 15 years. The average cost exceeds $2 billion, and roughly 90% of drugs that enter clinical trials never reach patients. A fault-tolerant quantum computer could change this picture fundamentally. It could simulate molecular interactions at true quantum mechanical accuracy, predicting how a drug candidate will behave in the human body before a single molecule has ever been synthesized in a laboratory. Drug development timelines that currently stretch to 15 years might compress to 3 or 4. Diseases for which there are currently no effective treatments could have multiple validated drug candidates identified and tested in simulation before a single human subject ever participates in a trial. The scale of preventable human suffering that this capability would address is almost impossible to quantify. Millions of people who will die from diseases that have no cure in the next decade might have been saved if quantum computers capable of molecular simulation existed today. The second major implication involves encryption, and this one does not have a hopeful cast. It is genuinely alarming. The security infrastructure of the modern digital world is built on a mathematical fact that has held true throughout the entire history of computing. It is computationally infeasible to factor a very large number into its prime components when the number is big enough. Breaking that factoring problem would take a classical computer longer than the age of the universe, even if you used every computer on Earth working simultaneously. Every time you log into your bank account, every time a sensitive government document is transmitted, every time a private message is sent through an encrypted application, the security of that communication depends on this mathematical assumption holding true. A sufficiently powerful quantum computer running a quantum algorithm called Shor's algorithm could break RSA encryption, the most widely used security standard in the world, in hours or even minutes. The implications are not merely financial. Military communications, intelligence agency operations, diplomatic correspondence, medical records, nuclear facility controls, All of it rests on encryption standards that a powerful quantum computer could tear apart. Governments have been aware of this threat for years. The United States National Institute of Standards and Technology has already finalized a set of post-quantum encryption standards designed to be resistant to quantum attacks. The concern has been about timing. If powerful quantum computers were still 30 years away, the transition to post-quantum encryption could proceed at a measured, organized pace. Now that the timeline for fault-tolerant quantum computation has contracted significantly, that transition becomes genuinely urgent. Organizations that handle sensitive encrypted data and have not begun planning for post-quantum security should not wait any longer. This is not a future threat. It is a threat that must be addressed before the capability to exploit it arrives. Beyond medicine and encryption, the implications extend into areas that may seem more abstract but are equally significant over longer time horizons. Climate science and energy technology stand to be transformed by quantum simulation capabilities. The behavior of materials at the atomic level determines properties like electrical conductivity, energy storage capacity, and catalytic efficiency. Right now, discovering materials with specific desired properties is largely a process of experimental trial and error, because accurately modeling how atoms in a material interact with each other is beyond classical computation for anything beyond simple structures. Quantum computers could simulate new materials from first principles with genuine accuracy, accelerating the discovery of better battery technologies, higher efficiency solar cells, and room temperature superconductors in ways that could fundamentally alter the economics of renewable energy. Those are not incremental gains. Any one of those discoveries could reshape global energy infrastructure within a generation. Quantum computing's potential effect on artificial intelligence is more speculative but worth considering. Classical machine learning already drives enormous advances, but it is fundamentally constrained by the mathematical operations that classical hardware can perform efficiently. Quantum machine learning is an emerging field exploring whether quantum algorithms can provide advantages in training, optimization, and inference for AI systems. The relationship between quantum computation and AI is not yet fully understood, but the possibility that quantum computers could open categories of machine learning capability that are fundamentally beyond classical approaches is taken seriously by some of the most rigorous researchers in both fields. Now, intellectual honesty demands a clear-eyed assessment of where things actually stand. The University of Chicago QLDPC blueprint is, at the time of this recording, a theoretical framework combined with early experimental demonstrations. The reconfigurable atom array hardware is real and actively being developed by Quera Computing and other organizations. But fully realizing the combination of QLDPC error correction with movable atom systems at the scale required for practical computation has not yet been demonstrated in a complete running machine. This is not a technology you can buy today. It is an engineering roadmap for a technology that the field is now racing to build with much greater confidence and clarity than it had before. The significance of the work is not that it delivered a working machine. It is that it delivered a credible, detailed plan for how to build one. Before this research, the quantum computing community knew that QLDPC codes were theoretically superior, but had no practical blueprint for implementing them in real hardware. After this research, there's a specific, physically grounded approach that connects the theoretical advantage to an actual building strategy. And when you have a real plan and the right people and resources to execute it, the transition from blueprint to working technology tends to accelerate rapidly. To put this historical moment in its proper context, consider what happened when the transistor was invented in 1947. At that moment, nothing about daily human life required a transistor. Nobody was clamoring for one. The practical applications were not immediately obvious to most people outside a small group of visionary engineers and scientists. And yet, within 50 years, the ability to manufacture and miniaturize transistors transformed virtually every dimension of human civilization. It gave us modern medicine, modern communication, modern transportation logistics, modern entertainment, and the entire digital economy. The transistor did not just make existing things faster or cheaper. It created entire categories of human activity and possibility that had not existed before. Quantum computing represents an equivalent inflection point. The path from where we are today to where this technology is headed will not be smooth or linear. There will be engineering challenges that take longer to solve than expected. There will be setbacks and course corrections. But the fundamental shift that the University of Chicago research represents is the shift from asking whether fault-tolerant quantum computing is achievable to asking what engineering approach will get us there first and how fast. Professor Fred Chong of the University of Chicago, one of the most respected and measured voices in quantum computing research, described this moment using a phrase worth pausing on. He called it escape velocity. What he meant is that quantum computing has now crossed the threshold where progress is no longer dependent on fundamental physics breakthroughs. The physics is understood, The hardware is advancing along clear trajectories. The error correction theory is now matched with a viable hardware implementation strategy. Building a genuinely useful, fault-tolerant quantum computer is no longer fundamentally a scientific problem. It is an engineering problem. And engineering problems, given sufficient talent, resources, and direction, tend to get solved. The QLDPC breakthrough is a massive contribution to that engineering path, but it is also not happening in isolation. The broader quantum computing landscape has been experiencing a genuine convergence of advances over the past several years, and understanding the context makes the University of Chicago work even more significant. Google demonstrated a critical milestone with its Willow quantum chip by showing error correction below threshold. This means that when you add more physical qubits to the error correction system, the overall error rate goes down rather than up. For years, this was the fundamental test that needed to be passed to confirm that quantum error correction could actually work in practice at system scale. Willow passed that test. IBM has simultaneously been advancing its own approach to reducing qubit overhead in fault-tolerant computation, announcing new error correction codes that lower the resource requirements compared to earlier approaches. Microsoft has been pursuing an entirely different physical approach, using a class of particles called Majorana fermions, which may have inherent resistance to decoherence. IonQ and Quantinuum, both using trapped ion quantum systems related to the atom array approach that underpins the University of Chicago work, have been demonstrating some of the highest quality quantum gates ever achieved in real hardware. Quera, the company directly connected to the Chicago research through its involvement in the published work, has been building and demonstrating atom array quantum processors with increasing scale and fidelity. What this convergence means is that the progress toward fault-tolerant quantum computing is not dependent on any single approach or any single team succeeding. Multiple independent paths are advancing simultaneously, each contributing to the overall acceleration. The University of Chicago QLDPC work is one of the most important contributions to that picture, but it is not a lone voice. It is one major piece of a genuine revolution that is unfolding across the entire field at once. For anyone living through this moment, the practical takeaways depend on who you are and what you do. If your work involves digital security or encrypted data in any form, whether you are in financial services, healthcare, government, or technology, the timeline for transitioning to quantum-resistant encryption has become significantly more urgent. The new post-quantum cryptography standards exist. The tools for implementing them are becoming available. The organizations that begin this transition now will be ready when the threat arrives. The organizations that wait until fault-tolerant quantum computers are demonstrated will be scrambling. If you work in pharmaceutical research, biotech, or any field connected to drug discovery, the next 15 years may look radically different from the previous 50. The integration of quantum simulation into the early stages of drug development, as fault-tolerant machines become available, could compress timelines and reduce failure rates in ways that have not been possible before. Following developments in quantum chemistry simulation and the partnerships forming between quantum hardware companies and pharmaceutical research organizations is worth serious attention. If you work in materials science, energy technology, or climate research, the ability to model new materials from quantum first principles is going to arrive within a generation and potentially much sooner. The first organizations to integrate quantum simulation into their research pipelines will have access to capabilities their competitors do not. And if you are not in any of those fields, if you are simply someone who wants to understand the world clearly and see where it is heading, this is one of the most important technology stories to follow right now. Not because the headlines will be dramatic every week, but because the decisions being made in laboratories and corporate research programs today will determine the shape of medicine, security, energy, and artificial intelligence for the next 50 years. The University of Chicago team did not hand humanity a finished machine. What they did was harder and, in some ways, more important. They handed the engineering community a credible blueprint that reduces an almost impossible challenge to an enormously difficult one. They showed that the obstacle which had blocked QLDPC codes from practical use, the problem of long-distance qubit communication, dissolves when you use hardware where the qubits themselves can move. They demonstrated that the qubit overhead for fault-tolerant computation is not fixed by physics. It is a function of the error correction strategy you choose, and a better strategy can change the game. 10 to 20 times fewer physical qubits to achieve the same computational result. A timeline that is compressed from 30 years to something that serious engineers believe the next decade might actually deliver. A direct connection between the academic research and a hardware company already building toward it. These are not incremental developments. They are the kinds of shifts that, looked back on from decades in the future, will be remembered as the moments when a technology moved from dream to destiny. Quantum computing has been promised many times. It has been overhyped and dismissed, championed and doubted in cycles that have stretched across entire careers. What makes this moment genuinely different is not that someone made a new promise. It is that the engineering path, once obscured and seemingly impassable, now has a door in it that was not visible before. The researchers at the University of Chicago found that door, and the people who build what comes next are already walking through it.